let's say that f of x is 1 over x squared minus 3x plus 3. And I'll let my domain be all real numbers. So again, like in the last example, I have no endpoints. There is no endpoints to D, so I can't add those to my critical points, but I do want to know what are the critical points of my function. So since I don't have endpoints, my only critical points are going to be interior. They're going to be where the derivative is 0 or it doesn't exist. So I'm going to think of this, since I'm going to take derivatives, I think it's easier to think of this as x squared minus 3x plus 3 raised to the minus 1. Then f prime will be the derivative of the interior. So I'm going to get a negative coming down from my power rule. Chain rule says I've got the derivative of the interior, which is 2x minus 3. And then on the denominator, I'll get the quantity x squared minus 3x plus 3 squared. So this is what the derivative is equal to. So we did the chain rule and power rule. So we took the derivative. This is our function, the derivative. And we want to know either when it's 0 or when it does not exist. Those would be the places where I would have critical points. So let's take 0 first. I've got a rational function. The only way a rational function could be 0 is if the numerator is 0. So first I'll look at when is negative 2x minus 3 equal to 0. And this is when x is equal to 3 halves. So there's a critical point. I can put it in here. 3 halves is a critical point. The other critical point could be where the derivative doesn't exist. Now, this is a rational function. The only place where it doesn't exist is where the denominator is 0. So to address where it doesn't exist, I look at the denominator and ask, well, when does x squared minus 3x plus 3 equals 0? Well, that's going to be when this polynomial is 0, and if I try to factor it, I can't get multiples of 3 to add up to negative 3. So let me use the quadratic formula. So this is when x is equal to negative b, so that's 3, plus or minus the square root of b squared, so that's 9, minus 4 times 1 times 3, all divided by 2a. So this is 9 minus 12, which is 3 plus or minus square root of negative 3 over 2, and this is imaginary. So there's no real value for x that forces the denominator to be 0, so there's no place where the derivative doesn't exist, and so we only have one critical value, namely 3 halves. So we've got one critical value. Great. Well, is it a maximum or is it a minimum of the function? So this is where we need to use the second derivative test again. So we've got to take the second derivative of f. We've got to take the derivative of this function. So let me scroll down. So f double prime, right, is the derivative with respect to x of negative 2x plus 3, all divided by x squared minus 3x plus 3 quantity squared. So I need to take that derivative. Now, here I do have a function on top, function on bottom, so I am going to have to apply the quotient rule. So this is equal to the derivative of the top. So the derivative of the top is negative 2 times the bottom. So that's x squared minus 3x plus 3 quantity squared minus this whole thing. So ends up being just plus 2x minus 3 times the derivative of the bottom. So I'm going to get excuse me, 2 coming down in the front for the power rule. So a 2. The derivative of this inside, so that's 2x minus 3. All times x squared minus 3x plus 3. And that whole thing then is divided by the denominator squared. So it's all divided by x squared minus 3x plus 3 raised to the 4th power. So this is what our second derivative is. It's this monster of a thing, but it's fine. We just need to evaluate it at our critical value. Our one critical value, recall, is 3/2. So this number, 3/2, we have to put into our second derivative function. So we look at f double prime of 3/2. And I won't bore you with the calculations. You can do it on the side if you really want to play with it. But this is equal to negative 32/9, which is negative, which tells us that f of 3/2 is a max. Or that 4/3, which is equal to f of 3/2, is the maximum value. Okay, so that's how we use the second derivative test. So let's look at one more general example before we move on to other types of extrema. Let's find the max and min of f of x equals the square root of 25 minus x squared, and our domain will be the interval from -5 to 5. And before we move on, let me kind of point out, you may find in Newton or other problems where they may not say max and min, they may say absolute max or global max. These are all equivalent statements. So the absolute maximum or minimum, the global max or minimum. These are all language that means the same thing. I want to find just the maximum value of my function and the minimum value of the function. The reason maybe these are used in other places is to distinguish from what are called local maximum or local minimum, which we'll look at in the next video. Back to this problem at hand. I want to find the max and minimum of root 25 minus x squared on the domain -5 to 5. So right off the bat, because we're on a closed domain, I know that my set of critical points will be -5 and 5. I need to investigate this to find out if I have any interior critical points. So to investigate, I need to take the derivative. So f prime of x is equal to -x over the square root of 25 minus x squared. So there's my derivative, and I need to ask, when is it 0, or when does it not exist? And since I do have a rational function, it's quite possible there's going to be places where this doesn't exist. So first things first, I'll look at the derivative. When is it 0? F prime of x equals 0. Well, this occurs exactly when -x equals 0, which is when x equals 0. So I've got a new critical value. I can put it into my list. I've got the endpoints, as well as a place where the derivative is 0. It's 0 when x is 0. And now to investigate, when does the derivative not exist? Well, that's when the denominator is 0, so or negative. So, but we know this is not going to be negative because we're on the domain -5 to 5. So we would be outside of this domain to make the derivative or the interior of the derivative negative. So we're safe there, but it is possible that we do have a 0. So when does 25 minus x squared equals 0? Well, this is exactly when x squared is equal to 25, which is when x is equal to plus or minus 5. And those are our endpoints. So we don't have any interior places where it doesn't exist. It only fails to exist on the boundary at -5 and 5. And so our whole set of critical values are -5, 5, and 0. And since we're looking for maximum and we have more than one, we can just go straight to the direct test. And so we evaluate our function on our critical values. So we'll look at c being -5, 5, and 0, and we'll evaluate our function f. At -5, it's 0. At 5, it's 0. And at 0, it is 5. And so we now know that the minimum value of the function is 0. This is the minimum value, whereas 5 is the maximum value. So we found our maximum, or again in other language, we found our absolute maximum, we found our global maximum, and they occurred at our critical points, either endpoints or places where the derivative is 0 or the derivative fails to exist. And so 0 is the minimum value of our function, and 5 is the maximum.